Volume by disk method. The disk method is a special case of the slicing method used with solids of revolution when the slices are disks. Suppose we have a curve y equals f of x in some interval from a to b as depicted in the diagram. If we rotate the curve around the x-axis by a complete revolution, the curve will map out the surface of a solid as it rotated. This is called a solid of revolution, as depicted in the diagram. We can see that the cross-sectional shape is a circle whose area is pi times radius squared, and the radius of each circle will be the value of the function at that point. Thus, the cross-section perpendicular to the axis of revolution is a circle of radius r, where r is f of x. The cross-sections of a solid of revolution are circles of radius r equals f of x and the area pi times radius squared. We calculate the volume of a solid of a revolution by using the basic defining formula. Thanks in advance for watching this video. If you liked this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. Find the volume of the solid obtained by rotating the region under f of x about x-axis from 1 to 4. The region above the x-axis is shown in figure. If we rotate about the x-axis, we get the solid shown in figure. When we slice through the point x, we get a disk with radius 1/2 times x plus 1. The area of the cross-section, then, is the area of a circle, whose radius is the function f of x. We now evaluate the integral above to obtain the volume. Find the volume of the solid obtained by rotating the region bounded by y equals x squared, y equals 1, and y equals 4 about the y-axis. The region is shown in the figure, and the resulting solid is shown in the figure. Because the region is rotated about the y-axis, it makes sense to slide the solid perpendicular to the y-axis, and therefore to integrate with respect to y. So we need to solve for x as a function of y. Since y equals x squared, the x equals square root of y. Notice that the region lies over the interval from 1 to 4 on the y-axis. We now evaluate the integral to obtain the volume. It's relatively easy to adapt the disk method to finding volumes of solids of revolution about a line that is not a coordinate axis. The next example should give you the idea. Pay attention. The line y equals 3 is parallel to the x-axis, so that cross-sections are the same as the cross-sections perpendicular to the x-axis. The radius of the cross-section extends from the line y equals 3 to the curve y equals x squared minus 2 times x. So, the length of a radius is the difference between these two values. That is, the radius of a circular cross-section perpendicular to the line y equals 3 is x squared minus 2 times x minus 3. By equating y equals 3 with y equals x squared minus 2 times x, we find the limits of integration. Finally, we integrate between minus 1 and 3 to find the volume. Calculate the volume generated by rotating an ellipse centered at the origin and the major axis on the x-axis around the x-axis. By rotating the ellipse around the x-axis, we generate a solid of revolution called an ellipsoid, whose volume can be calculated using the disk method. We start by writing the standard form of the equation of an ellipse at the origin and the major axis on the x-axis. We can find the radius of the cross-sections of an ellipsoid by solving the equation of the ellipse for y. We get the volume of the ellipsoid by integrating from minus a to a.